Welcome everyone to the E3SM All Hands webinar. Today, Jim Benedict is speaking. Jim received a PhD in atmospheric sciences from Colorado State University in 2010. And after that, he worked with Bill Collins at Lawrence Berkeley National Lab and then at the University of Miami. And he joined us at Los Alamos National Lab in 2020. And this is part of the series on the SIDAC projects. And I'll let you go ahead.
All right, thanks, Mark. So yeah, as Mark said, this is one of 7 SIDAC 5 projects that are that were awarded last year, and the one that I'm working on and leading is improving the QBO through surrogate-accelerated parameter optimization and vertical grid modification. So for personnel, we have a good group of people. We have people from Livermore, Los Alamos, Sandia, and NCAR. And we have a mix of, as per the SIDAC projects, we have a mix of BER funding for climate-related tasks and OSCAR funding. And so our OSCAR membership is Fast Math members, and those are situated at Sandia. So that's Mike Eldred, Bert Deboucher, and Hachik Sargsayan. And we also have a good mix of senior and junior scientists, as well as a number of postdocs working on this project. So we're happy to have that breadth of knowledge. I should also mention that we have collaborations with community QBO working groups outside of just our immediate SIDAC project. And we're also collaborating and doing knowledge transfer with the climate auto-tuning efforts at Sandia, led by Andy Salinger. So what is the QBO? The QBO is a mode of variability in the tropical stratosphere. It's identified by alternating phases of equatorial zonal mean zonal wind. So it's an alternating easterly and westerly winds with a period of about 28 months. And you can see this in the plot on the left. So if you took the zonal mean zonal wind and you plotted it over time, so time is on the x-axis and pressure is on the y-axis, you can see this pattern develop where you have this alternating westerly in the red shading and easterly in the blue shading winds. And these wind extrema and their shear zones, so where the zero line is, they migrate downwards slowly with a period of 28 months, as I mentioned. This pattern is driven primarily by momentum deposition from convectively generated gravity waves. So think tropical convection is radiating gravity waves upward, and they propagate into the stratosphere and they break and they deposit momentum in the stratosphere, and that's what ultimately drives the QBO. The QBO has large global impacts. It impacts extratropical weather, tropical convective variability, which is obviously local to the tropics, and also the distribution and transport of stratospheric tracers. So an accurate QBO representation in global climate models remains a significant challenge. Some of the factors involved in this challenge are you need to sufficiently resolve in the vertical the waves that are propagating and breaking in the lower stratosphere. This is required to capture this wave propagation and breaking and the momentum deposition that's associated with that. The second thing is you also need to adequately represent tropical synoptic atmospheric waves. So these are resolved on the grid scale, and this can include things like atmospheric Kelvin waves and mixed Rossby gravity waves. The model also needs to adequately represent convectively generated gravity waves. So these are unresolved processes. Now the QBO, the forcing or the driving mechanism of the QBO is about 50% from these resolved synoptic waves and 50% from the convectively generated gravity waves. So a recent study showed that of 30 CMIP6 models examined, only 15 were able to produce a reasonable QBO. But even those that did failed to accurately capture the QBO amplitude, or other aspects of the QBO were undesirable. In the alarming news is that in E3SM v2 and the current development version of v3, that they failed to produce what we would consider to be a reasonable QBO. So that's part of the motivation for this project. So let's take a step back and see how we got here. An accurate representation of the QBO amplitude and period in E3SM remains elusive. So I showed this earlier. This is the ERA interim observational pattern of the QBO over the AMIT period. So in version 1, E3SM v1, we had a higher frequency of this pattern, and the amplitude was also higher. So tuning was done by colleagues at NCAR who are part of this SciDAC project, and they were able to modify the gravity wave tuning scheme to better represent the pattern, the observed pattern of the QBO. So when these effective gravity wave and convective fraction tuning parameters were then applied subsequently to E3SM version 2, the improvements seen by the tuning were rolled back. So essentially what happened was, in V2, initially we got back what looked like the V1 pattern of QBO amplitude and period. So additional tuning was done to try to get back the improved QBO representation in V2, and that's what you get on this bottom panel here. So obviously the period, arguably it's okay, but the amplitude is too weak compared to observations. And we think why this sort of degradation happened is potentially partly due to the changes in the V2 deep convection scheme. And so we're looking into that now as to why that would have an effect on the QBO. But the main message is that the amplitude remains too weak for the QBO in V2. So the good news is that the representation of the resolved scale convection distribution dramatically improved in development V3, between V2 and V3. So Jack Chen at NCAR has installed his mesoscale coherent structure parameterization. This essentially represents organized tropical convection on mesoscales. That, in addition to the microphysics changes, has improved subseasonal tropical convection, as shown in the plot on the left, but I won't get into the details due to time constraints. So unfortunately, the QBO in development V3 remains weak. So we tried to do a session of manual tuning on V3 to improve the QBO, but that was much less successful than it had been in V1 or V2. So we're struggling with that right now, but we have a solution that thoroughly. Anyways, of the tropical convection in the model is adequately represented, but so this implies that this is a necessary but not sufficient condition for an acceptable QBO. Some portion of the forcing is improved, but the QBO remains very weak. And this further suggests that the vertical grid resolution and the gravity wave parameterization may be the weak links. So a second task that we're involved in is doing model calibration and beginning to use a surrogate-accelerated parameter optimization. So what Jack had done for his manual tuning exercise was confined to this lower left portion of the graph. So this is the convective fraction normalized value on the x-axis and another parameter, effective gravity wave, on the y-axis. And so we began to further explore the parameter space to try to understand the sensitivities of the QBO to the tuning. And the end result is that we found that there was limited success in our tuning, even though we explored the full parameter space in the parameters that we thought had the largest impact on the QBO, this didn't improve the QBO that much. And so so this is sort of a dead end at this point, but we have other alternative solutions to consider. So in addition to exploring the parameter space, we're also refining the surrogate model itself for uncertainty quantification or UQ analysis and parameter optimization. So the colleagues at Sandia have developed workflows to demonstrate dimensionality reduction, the surrogate construction itself, as well as Bayesian inference on a test data set that had really no motivation to change the QBO. It was an existing data set that we had available to us. And so we used it to just develop our workflow, but we're going to apply it soon to more QBO relevant ensembles of simulations. So the basic workflow for the surrogate model development is you have some set of E3SM simulations. You send them, or you can take the output from there and train surrogate models to map the climate inputs to the QBO output. So essentially the parameter values to QBO metrics or quantities of interest. And then you can use the provisionally optimal parameters to rerun E3SM and verify if you've actually gotten real improvement in the QBO metrics. And so this is an iterative process. And you can, along the way, you can also refine the surrogate model itself, which is some of the work that's going on right now. The end result, hopefully, is an optimized QBO. So another task that we're doing, if you recall, we know that the QBO is sensitive to the gravity wave parameterization, which is controlled mostly by the tuning parameters. But I also mentioned that the vertical grid resolution is potentially equally or more important. So we tested this. We tested this initially with V2 because that's what we had. This goes back several months now. We tested the vertical grid resolution in the lower stratosphere. So you can't really see this black line, but this black line here follows straight down here. So this is a plot of grid resolution or grid spacing on the x-axis, and the approximate pressure, the nominal pressure, is on the y-axis here. So you can see that in the troposphere, the vertical grid resolution is roughly 600 meters or so. And that goes up to the lower stratosphere, but then it abruptly coarsens above that. Oops, sorry about that. It abruptly coarsens above that. So the grid spacing gets much coarser as you go up. So we were concerned about this given that the QBO operates in the lower stratosphere. And also we need to resolve the vertically propagating gravity waves, which have a relatively small wavelength. So we tried two things. The first is we tried to smooth out this kink. So that's this red line here. We didn't change the total number of levels. We just smoothed the grid, or we smoothed the change in the grid resolution. And so that shows modest improvement to the QBO. So that the control simulation is at the top here. This is the same time on the x-axis and pressure on the y-axis. And I'm showing zonal mean, zonal wind. So you can see that there's really no QBO pattern here whatsoever. If you smooth the grid, you have some resemblance of the QBO pattern beginning to emerge. If you add 8 layers to the lower stratosphere, which we did in our second attempt, so this is the blue line now. So we just extended the tropospheric grid resolution up further into the stratosphere. And then we also did some limited smoothing on top of that. When you do that, you get a much more robust QBO amplitude. Now, this is not perfect, obviously, because we found that the period is a little bit different. And I'll get into more details of this in a second. We found that the period is a little bit different. We also found this persistence of westerly winds where the QBO is most active. And that's not the most desirable thing to have, but the amplitude of the QBO is much improved. I'm going to say that the added cost is about 5 to 6%, but recent tests on Chrysalis show that it could even be less than this. And we can talk more about that if someone has a question about that. It's a little bit confusing. I don't think it's more than 5 or 6%, but it could be significantly less than that. Okay, I'll move on, and we can circle back to that if someone has a question about that later. So a bit more on the 80 level version of E3SM version 3. We think this is potentially of interest to some of the model developers on the call. So we ran 2 tests. We took V3 Alpha 02, a historical simulation, with the default 72 levels, and we compared it to an 80 level version. The 80 level version has 8 layers that are added to the lower stratosphere. This is exactly what I described in the previous slide. So we just added a few layers in the lower stratosphere. All other parameter values and model configuration is identical other than the 8 added layers. The time and cost, we can talk about that again later, but we think it's about 5 to 6%. The full E3SM diagnostic output is shown in these links, which will be posted on the Confluence page for this all hands webinar. And people can look through them, but I'm going to show some key results from them right now. So the ultimate goal is to improve the QBO and not change the climate. So we'll see what happens here. So let's look at the QBO first. So these are probably familiar to most of you, but these are diagnostic plots of the QBO. And I'll ignore the pattern plots here, and let's just look at, this is QBO amplitude. So the amplitude is on the x-axis here, and then this is pressure on the y-axis. So in observations, you have the peak QBO amplitude is somewhere around 20 to 30 to 40 hectopascals, somewhere around here, at about 25 meters per second. The 72-layer version of V3 does not have that. It's much, much too weak. And if we look at the period, so now the period is on the x-axis on this lower left plot. The period is the amplitude is so weak that the period is difficult to assess. Let's just say that. If you go to the 80-layer version of the model, you have a dramatic improvement in the QBO amplitude. The period is much easier to assess, and it's a little bit lower than the ERA interim product. But it's not bad. It's probably about 25 months or so. So let's look at the climate now. In short, the tropospheric climate shows no degradation, and I would argue that the differences are basically negligible when you add these 8 layers to the lower stratosphere. This is not too surprising, given that the layers are added only to the stratosphere and not to the troposphere. But if you look at precipitation, so L80 is on the top row, L72 is in the middle, and the difference is on the bottom. The precipitation differences are very small, and there's no systematic pattern. The same is true for restom. For surface pressure, there is an increase in surface pressure in the Antarctic region, but it turns out that this is actually a reduction in the difference between L72 and the observational product. So this is not a degradation. This is actually an improvement if you believe the observations over the South Polar region. And then the zonal wind at 200 is also not changed. So I've shown that there's thermodynamic, radiative, and then dynamic changes. They're virtually not much. There's not much to say about them. And so now I'm going to compare the L72 with the observations, GPCP observations. And we can see the difference between the model and observations here. I just want to demonstrate that the difference between L80 and L72 is much, much smaller than the difference between the model and observations. So there are differences in the stratosphere, the mean climate of the stratosphere. And we're just beginning to dig into these now. And we would like help. So we'll probably reach out to some of you on this call to do that. The ozone, so this is ozone on the left column here, L80 on the top, the 72 layer version of the model in the middle, and the difference on the bottom. So there is an increase, no, sorry, there's a reduction in ozone in the L80 version of the model along the equator. And then outside of that, poleward of that, there's a slight increase in ozone by about 2%. So there's a 7% reduction here. The zonal wind does change, and this is one of the main differences that we see. We haven't really dug into this yet, but there's an acceleration of the westerlies in the lower stratosphere that we're looking into now. We sent our results to Ziming, and he was looking at stratospheric sulfur burden. Apparently, this is the Pinatubo eruption, I guess. So L72 is the red line on the top, and L80 is the red line on the bottom. If you look really closely, you can see that there's a slight reduction in the stratospheric sulfur burden. Okay, so the final notes on L80. The MJO is slightly weaker. So L72, this is a lag correlation of the MJO part of E3SM diagnostics plot here. So L72 is on the left. This is precipitation and zonal wind. I won't get into the details, but basically you can see some subtle differences, especially the blue shading down here. This is the easterly winds. It's a bit more disrupted. Now, that's actually expected because the L80 has a stronger preference for a westerly QBO phase, and the westerly QBO phase in nature disrupts MJO propagation and weakens it slightly. So this is actually an encouraging result, even though it's a slightly weaker MJO. We haven't yet looked at the diurnal cycle, and we haven't looked at other modes of variability. So I know I've been saying that the climate doesn't change, the tropospheric climate doesn't change, but the mean state doesn't change, but the variability might, and that's what we need to look into. So in summary, despite the improved tropical convective variability in V3, now this is for the 72 layer, the default 72 layer version of the model, we have an improved tropical convective variability, which is a driver, contributes to QBO variability, but the QBO remains weak. So that's indicating that the parameterized gravity waves or the vertical resolution is sort of the weak link in this chain. We added 8 layers to the lower stratosphere, and we found a dramatically improved QBO amplitude. This is untuned. I should say this we haven't done any tuning yet on that. Manual tuning efforts for V3 have had limited success. Now we know that surrogate-accelerated parameter optimization can help with this, but in this particular case, we found that we can't tune our way out of this problem. So the next steps are we want to do obviously more evaluation of the L80 simulations that we have. We're going to run new simulations and feed them into the surrogate model in an attempt to optimize the QBO in L80. And we're hopeful that what I want to say is we have a QBO to work with. In the previous version with L72, there was no QBO to work with, so the tuning didn't really matter. It didn't really do much. But now at least we have a viable starting point for which we can tune and hopefully optimize QBO in V3. And the final point I want to make is we're offering this possibility to the E3SM developers. If you are interested, you can contact us and we'll work with you to try to implement this into the model if that's viable. I know there's a long list of other things that are going into the model. But if it works, it works, and if it doesn't, that's fine. We sort of did our due diligence, and this is what we got. So if anyone has any questions, please feel free to ask.
Okay, great, thanks.